Look up at the skyline of Qianhai on the western edge of Shenzhen, and something is missing. It is a summer afternoon in 2024. The temperature is pushing 35 degrees Celsius. The humidity is brutal, and the glass towers here are packed with people. Yet the rooftops are almost bare. There is no forest of boxy condenser units. No window air conditioners bolted to balconies. No rattling metal fins dripping onto the sidewalk. In almost any other city on Earth, a district this dense would wear tens of thousands of separate air conditioners like scales, each one grinding away, each one pumping its own hot exhaust back into the street. Multiply that by every building and you get the low, constant roar that hangs over most modern cities in July. Here, in Qianhai, that roar is gone. The buildings barely hum. Somewhere out of sight, a hidden machine is doing the work of 100,000 air conditioners at once. And still, behind the glass, something is keeping millions of square meters of floor space cold. Office towers, shopping centers, exhibition halls, all of them sitting at a comfortable 24 degrees while the pavement outside bakes. So where is the machine? You cannot see it on the roofs, you cannot hear it on the streets. That is because it is not in the buildings at all. The cooling for this entire district has been pulled out of the towers, gathered together and buried underground, in a handful of large stations connected by insulated pipes running beneath the roads. Instead of thousands of small machines fighting the heat one apartment at a time, Qianhai fights it as a single system. It is a way of cooling a city that almost no existing city could copy, because it had to be decided before the city was built. To understand how Shenzhen ended up with a skyline that barely sweats, you have to go back to a stretch of empty, reclaimed marshland and to a decision made in 2014, a decision most urban planners never get the chance to make. Rewind 10 years to 2014. The place we now call Qianhai is barely a place at all. It is a bay of reclaimed land on Shenzhen's western edge. 15 square kilometers of silt and seawater dredged and filled to make new ground where there was once only shallow water and marsh. There are no towers yet, no malls, no offices, no streets full of people, just graded earth, survey markers, and blueprints. And that emptiness is the whole point. Because in 2014, the planners drafting the Qianhai Cooperation Zone were handed something almost no city government ever gets: a blank slate the size of a district, and the authority to decide how it would work before a single foundation was poured. Most cities inherit their problems. They grow building by building, decade by decade, each owner installing their own heating, their own plumbing, their own air conditioning, until the result is a patchwork nobody designed. Cooling, in particular, is almost always an afterthought, bolted onto each structure separately, one condenser at a time, long after the walls go up. Qianhai's planners made a different call. They decided to treat cooling not as each building's private problem, but as shared infrastructure for the entire zone, like the water mains, the power grid, or the subway. Before the district existed, they drew cold into the master plan itself. That meant reserving underground corridors for pipes. It meant setting aside land for large cooling stations, while land was still cheap and empty. It meant requiring that towers, when they were finally built, would connect to a district network instead of sprouting their own rooftop machines. Deciding this in 2014, on empty ground, is what made everything that followed possible. You cannot easily retrofit a plan like this into a finished city. You have to commit to it before the concrete. So what exactly did they commit to? To understand the scale of the bet, you first have to understand what district cooling actually is, and why one shared source of cold can replace thousands of separate boxes. Here is the ordinary way a city stays cool. Every building fights the heat alone. An office tower might carry hundreds of individual air conditioners. A shopping mall, its own bank of chillers on the roof. An apartment block, a window unit rattling in every flat. Each of these machines does the same 3 jobs over and over. It makes something cold, it blows that cold into the rooms, and it dumps the leftover heat outside. Thousands of little engines, all duplicating the same work within a few hundred meters of each other. It is enormously redundant. Every unit needs its own compressor, its own maintenance, its own patch of roof or wall. Most run flat out only a few hours a day, then sit idle, expensive hardware, mostly waiting. And because they are sized for the hottest possible afternoon, the city pays to install far more cooling capacity than it ever uses at once. District cooling throws that whole model out. Instead of thousands of separate boxes, you build a few large central stations, call them cooling plants, and you concentrate all the heavy machinery there. Those stations chill water down to near freezing, around 4 or 5 degrees Celsius. Then, instead of moving cold air, you move cold water. The chilled water is pumped out through insulated pipes buried under the streets, flowing to every connected building in the district at once. Offices, malls, hotels, exhibition halls, government buildings, all drinking from the same cold source. Think of it as replacing thousands of little wells with a single river of cold. When the water reaches a building, it passes through a heat exchanger, absorbs the building's warmth, and returns to the station a few degrees warmer to be chilled again. The tower itself needs no compressors, no rooftop machines, no rattling condensers at all. The advantage is not just tidier rooftops. Concentrating the work in a few large machines is dramatically more efficient than scattering it across 10,000 small ones. But to see why, you have to go down into one of these stations and stand next to the machinery that makes the cold. Step through the doors of a Qianhai cooling station, and the first thing that hits you is the sound. A deep, steady mechanical drone and the feel of cold, damp air. This is where all the cooling the district removed from its rooftops has been gathered into one room. The heart of the station is a row of industrial chillers, machines the size of buses, each one a giant version of the compressor humming in a household refrigerator. Inside them, a refrigerant is compressed, condensed, and expanded in a loop, and every time it expands, it pulls heat out of the water flowing past it. Cycle after cycle, the chillers drag the water's temperature down toward freezing, to roughly 4 degrees Celsius. That near-frozen water is the whole product of this building. Next to the chillers stand banks of pumps. Powerful electric pumps, whose only job is to push that cold water out into kilometers of pipe and keep it circulating through the entire district, around the clock. But making cold has a stubborn side effect. You cannot remove heat from one place without dumping it somewhere else. The heat the chillers pull out of the district has to go somewhere, and that is what the cooling towers on the roof are for. Warm water from the machinery is trickled through them while fans and open air draw the heat off through evaporation, releasing it to the sky as a faint plume of vapor. Between these systems sit the heat exchangers, sealed banks of metal plates where two streams of water flow close together without ever mixing, so heat can pass from one loop to the other. The district's water gets chilled. The machinery's water carries heat away to be rejected. Chillers, pumps, heat exchangers, cooling towers. Together they turn ordinary electricity into a river of cold water and a plume of waste heat. It is a lot of power to run all at once, and electricity is most expensive and dirtiest, exactly when everyone wants cooling most, the blazing middle of the afternoon. So Qianhai's engineers added one more trick, a way to move that demand in time. A battery, but not the kind you would expect. The trick is ice. In a corner of the cooling station stand enormous insulated tanks, and at night they fill with ice. Here is the logic. Electricity is not priced the same around the clock. In the small hours, say from midnight to dawn, demand across the grid collapses. Power plants have spare capacity, and electricity is cheapest and often cleanest. In the afternoon, when every office and mall is calling for cooling at once, demand spikes, prices climb, and the grid strains to keep up. So Qianhai's engineers do their hardest work at the wrong-looking time. Overnight, while power is cheap, the chillers run hard, not to cool the district, which is mostly empty, but to freeze thousands of tons of water solid inside those storage tanks. The station is charging a battery, but instead of storing electricity and chemicals, it stores cold in ice. Then the afternoon arrives. The sun is high, the towers are full, and the demand for cooling peaks. Now, instead of forcing the chillers to run flat out against the most expensive power of the day, the station simply melts its ice. Warm return water from the district is run past the frozen tanks. The ice absorbs its heat and melts, and chilled water flows back out to the buildings, all with the chillers throttled back or off. The cold was made hours ago, at night, and saved. Engineers call this thermal energy storage, or an ice battery, and its payoff is in one word: peak. By shifting the heavy electrical load from the crowded afternoon into the empty night, the station flattens its demand curve. It draws power when the grid has plenty to give and stays quiet when the grid is straining. That means lower electricity bills, less stress on the city's power supply, and cleaner energy, since off-peak power often leans more on baseload and renewable sources. A block of ice, in other words, lets the whole grid breathe. But making cold in a central station is only half the problem. Once the water is chilled or the ice is melted, it still has to travel, unseen, all the way to every building in the district. Leave the cooling station and follow the cold underground. Beneath Qianhai streets runs a second city, a lattice of steel pipes wide enough to crawl through, wrapped in dense insulation and buried in utility tunnels, poured during construction. 2 pipes shadow every road, a supply line carrying chilled water at roughly 4 degrees Celsius, and a return line bringing it back near 12, warmed by the heat it collected along the way. Pumps push this water for kilometers, out from the station and into the base of every connected tower. Notice what is missing. There is no chiller on the roof of the office block. No condenser rattling outside the shopping mall. No compressor humming in the basement of the concert hall. Each building's mechanical room holds only a heat exchanger, a quiet steel plate the size of a wardrobe. On one side flows the district's cold water. On the other flows the building's own loop. They never mix. Heat crosses the metal wall, the building's water goes cold, and that chilled water fans out through the tower's air handlers to cool every floor. When the cold has done its work, the district water flows back down the return pipe to the station to be chilled again, an endless circuit turning under the pavement. This is why the buried, pre-planned network is the whole idea, not a detail. You cannot easily tunnel these lines under a finished city. In Qianhai, the trenches were dug before the towers rose, the tunnels cast alongside the foundations, the connection points stubbed out and waiting. A building arrives, plugs into the loop, and inherits cooling on day one, no rooftop plant required. The distribution is the product. The stations are only its source. And once the pipes are in the ground, the logic of the system flips. A single line can feed 100 towers, so the more buildings that connect, the cheaper and denser the cold becomes. Which raises the obvious question of scale. How many stations, how much water, how many square meters can one buried network actually carry across an entire district? By 2024, the answer had a shape. The Qianhai Cooperation Zone was built around a network designed for roughly 10 cooling stations, each a hub and a web of underground pipe, together engineered to chill millions of square meters of floor space. Put that number in a body you can feel. Millions of square meters is not one skyscraper. It is a whole downtown of offices, shopping centers, hotels, and public halls. An entire district of glass towers whose cold all traces back to those 10 stations instead of to tens of thousands of individual machines. Consider what that consolidation replaces. A conventional district this size would wear a crown of rooftop chillers and condensers, one cluster per building, each sized for its own worst afternoon, each running whether its neighbor needed cooling or not. Qianhai deletes almost all of them. The cold is made centrally, at industrial scale, by large chillers that run far more efficiently than the small units they retire, and it is made where it can be managed as one system rather than thousands of stubborn islands. The payoff shows up in 3 places. First, peak electrical load falls, because a shared station sized for the district's combined demand needs less capacity than every building bracing alone for its own peak. Second, the rooftops come back. Stripped of their mechanical crowns, they open up for gardens, solar panels, terraces, or simply cleaner skylines. Third, the electricity bill shrinks because bigger machines, smarter scheduling, and the ice storage from the night before together cut the power a scattered fleet of standalone units would have burned. 10 stations, millions of meters, one coordinated cold utility humming beneath a district that barely seems to have any cooling at all. It is a genuinely elegant piece of engineering, and reading it, the temptation is to assume every city should simply do the same. But Qianhai's success rests on conditions most cities do not share, and the honest engineer has to ask the harder question. If district cooling is this good, why isn't it already cooling everywhere? The honest answer is that district cooling is not a universal upgrade. It is a specialist that thrives only under conditions Qianhai was lucky enough to design in from the start. 3 of those conditions matter most. The first is density. Chilled water loses cold to the ground as it travels, and every meter of insulated pipe costs money to lay and to pump through. When towers stand shoulder to shoulder, a short run of pipe can serve enormous floor area, and the numbers work. Spread those same buildings across low suburbs, and the pipe grows longer, the losses grow larger, and the economics collapse. The second condition is simultaneous demand. A central station is efficient because a downtown of offices, malls, and hotels all want cooling at roughly the same hot afternoon, letting one shared plant serve many customers at once. A neighborhood of houses, cooling in scattered bursts through the evening, never lines up that way, so the station would sit half idle and the shared advantage disappears. The third condition is timing, and it is the hardest to fake. Qianhai buried its pipes and tunnels before its towers existed. A city that already stands cannot easily do that. Retrofitting district cooling into a finished neighborhood means tearing open live streets, threading pipe past century-old water mains, gas lines and subway tunnels, and persuading hundreds of separately owned buildings to rip out working chillers and connect to a shared loop, all at once, for a payoff that only arrives when enough of them say yes. That is why you see district cooling in Paris under the Seine, in central Stockholm, in the Gulf's planned business bays, and in new Chinese zones like Qianhai, and almost never stitched into a sprawling, already built old city. It is not that the technology fails there. It is that the pipe density and the shared peak that make it cheap simply are not present. So the lesson of Qianhai is narrower and sharper than universal comfort, and it points at a specific kind of future city, one worth looking at directly. Step back from Qianhai and look at the century it belongs to. The planet is warming, and at the same time, humanity is moving into cities faster than at any point in history. By 2050, roughly 2/3 of the world will live in urban areas, most of them in the hot, fast-building regions of Asia, Africa, and the Middle East. Cooling, once a luxury, is becoming survival. The International Energy Agency projects that the number of air conditioners worldwide could triple by 2050, adding billions of individual machines, each drawing power on the same brutal afternoons, each pushing waste heat into streets that are already too hot. Left to the old pattern, that is a spiral. Hotter cities buy more air conditioners, which draw more power and radiate more heat, which makes the cities hotter still. Qianhai is a small, concrete argument that the spiral is not the only option. It does not claim to cool every place. We have just seen why it cannot. What it proves is narrower and more useful, that when a district is dense enough, planned early enough, and demanding cooling all at once, there is a smarter unit of cooling than the single room. You can chill water at 10 stations, store cold and ice overnight when the grid is cleanest, and pipe that cold to millions of square meters at once, retiring tens of thousands of rattling boxes and reclaiming the rooftops they used to crowd. As the world designs the new cities it is about to build, The choice Qianhai's planners made in 2014 stops looking exotic and starts looking like a template. Do not hand every tower its own machine and its own peak and its own waste heat. Build the cold once, share it, and bury the network before the towers rise. The city that barely hums, the one we opened on, is what that choice sounds like from the street. And that is the whole idea of Qianhai, distilled to a single instruction for the warming urban century ahead. Cool the district, not the room.